today's video, we're going to talk about ray-traced reflections. Before we begin, it's important to understand the other techniques we can use for creating reflections. We'll talk about how they work and what their weaknesses are. Then I'll show you how to turn on ray-traced reflections in Unreal. And we'll talk about how ray-traced reflections fix the weaknesses of the other methods. Finally, we'll go over each of the settings for controlling the ray-traced reflections, and we'll talk about what they do and how they affect the visual quality and performance of the scene. So let's get started. Alright, so here we are in Unreal, and you can see that I've loaded up our subway car demo scene. And I've also added some spheres down here at the end that are really reflective to kind of help to show off some of the principles that we're going to talk about today about reflections. So the first thing that we want to talk about is reflection probes. That's the first method for adding reflections to your scene. And you can see here that this scene comes with a whole bunch of reflection probes already. Now what these are points that you place into the scene, and a cube map is captured from that specific point. And then that cube map is used as the reflections. You can see if I toggle on these reflection probes, all the reflections turn off, and when I toggle them back on, all the reflections turn back on. So if I select all of these, you can see the little UI widgets that indicate where the probes actually are located, and also the radius that's used to determine how much influence the probes have over the scene. So for each probe, if I'm inside this radius for the specific probe, I'll be looking at the reflections from the cube map that probe provides. So this is a pretty good method for reflections. Light probes have been around for a long time. We've been using cube maps for reflections all the way back to GeForce 2 days. Now there are some weaknesses to this technique. Let me just unselect our probe volumes here. One of the weaknesses is that the probe is only accurate from the specific location where it was captured. So if I take a look at these spheres, the reflections in every sphere look exactly the same. Even though the spheres are in different locations, like for example, you would expect for this one to be reflecting this seat that's underneath it, but it's not. It's just showing the reflections for the nearest probe capture, which is somewhere around here. So all of these reflections look the same, even though they're in different locations. So that's the first weakness of probes. And I can show you another example. If we come out here outside the train, and I come over here to this probe. So this probe is in a location where it's not inside the radius of any of those probes that are inside the train car. And you can see that there's some really weird reflections on this one. I can see both the front and the back side of the train. And if I select my probes again and come over here, you can see why. See how it's outside the radius of these probes? And the only probes that touch it are this one here in the front of the train and this one here in the back of the train. And so in this location, we only see reflections from the front and the back of the train, even though we should be seeing reflections from this side of the train. And that brings us to the next weakness of reflection probes, and that is it takes a lot of time to place these. Somebody's gone through and spent a lot of time figuring out exactly the correct locations for each of these probes, and also exactly the correct radiuses to use for each of the probes as well. So there's a lot of effort required in placing these down. And the third weakness of these reflection probes is that they're static. Those cube maps require baking, and so anytime that I change my scene, I'm going to have to rebake the probes. So I spend a lot of time rebaking lighting, rebaking probes with this method of reflections. And the final weakness of these reflections is there's nothing dynamic in them. Because they're baked, anything that's moving in my scene is not going to be captured in my baked light probes. All right, so that's a pretty good summary of light probe reflections. The next kind of reflection we're going to be taking a look at is screen space ray tracing, or screen space reflection. So let's come here to our post-process volume, and I'm going to come here to screen space reflections. I have their intensity turned all the way off for now, just so that you can see the contribution of just the light probe reflections. But I'm going to come over here and I'm going to turn the intensity of our screen space reflections on. And you can see here, as I turn them on and off, what a difference the screen space reflections, or the screen space ray tracing, is making. So let me take a minute to describe what's happening here. With screen space ray tracing, basically the game takes the screen and reconstructs the scene based on the depth buffer. And then, instead of shooting the reflection rays into the cube maps from the probes, it actually shoots the rays into the reconstructed scene that it's made from the screen. And so you can see here, I have reflections like this sphere here is reflecting its neighbor, and it's reflecting seats down here from the scene. So anything that I can see on the screen can also be included in the reflection. This is a form of ray tracing, but it's vastly simplified because it can only include what's on the screen. So nothing off to the side of the screen or behind the camera can be ray traced. And so what happens with this form of reflections are anything, any area that would be reflecting something that's off screen falls back to the light probe reflections instead. So if we're looking at the sphere here, the area in the center here that would be reflecting stuff behind me is using the cube maps, the light probes, and anything around the edges where it can capture reflections from the screen is using screen space reflections or screen space ray tracing. So screen space ray tracing is great because it's dynamic, it can capture moving objects, and it also doesn't have to be baked, unlike light probes. Screen space ray tracing is dynamic, it's happening in real time. But it does come with its own set of problems. Because it's only capturing things that are on the screen, when we move around and change what's on the screen, you can see that the reflections are actually changing, which is kind of weird. Especially weird if I look down and all of a sudden the parts of the screen that were being reflected are no longer visible. This is especially true if you're using screen space ray tracing for water. And if you're looking straight ahead, you can see the sky. But as soon as you look down into the water, the sky in the reflection completely disappears. And that's kind of a big deal for reflections when you're having this issue with things changing all of the time. So anyway, so we have light probes or cube maps, and we have screen space reflections or screen space ray tracing, which are the two types of reflections that we're currently using. Now what I want to do is turn on ray traced reflections and show you how ray traced reflections can solve these problems. So if I come over here to the post-processing settings, I'm going to close down the screen space reflection settings and just come up here to the general reflection settings, and you can see here I can choose between the type of reflections that I want to use. I can choose screen space or ray tracing. These two methods are mutually exclusive. So instead of screen space, I'm going to choose ray tracing, and immediately you can see that all of the artifacting that was looking kind of weird with the screen space reflections has gone away. And now if I come over here, you can see some new properties in our reflections. For example, if I'm looking here at this probe, it's reflecting this bench that's below me. So this bench is actually off screen when I'm looking at the probe, but it's still reflected in this sphere because I'm actually ray tracing this object that's off screen to apply as the reflection. Really cool. And you can see that the reflections on every one of these spheres is different, and it's unique, and it's actually physically correct for the scene because I'm tracing rays into the scene and even capturing parts of the scene that are behind me. Ray trace reflections are also really cool because they're dynamically generated. Anything moving in the scene is going to be captured in the reflection. For example, if there's a player character, I can see myself reflected in these reflections, and that wouldn't work for screen space reflections or for probe reflections. And finally, because the ray trace reflections aren't baked, they're completely dynamic. And you can see if I grab a sphere and move it around, these reflections are updating in real time, and there's no baking involved. So I don't have to do all kinds of work to place light probe volumes or rebake them when the scene changes. These reflections are rendered real time in the scene, and they just work really beautifully. Okay, let's take a look at some of the settings that we can use for tuning the ray tracing. So I'm going to come down here again to my post-process volume and open up the ray traced reflection settings. The first setting that I want to go over is max roughness, and in order to illustrate what's happening with that setting, I'm going to come over here to this set of spheres. Now what I've done here is for each of these spheres I've set up reflections with different roughness. So this sphere over here on the right has a roughness of 0, or a perfect mirror. This one has a roughness of 0.1, 0.2, 0.3, and 0.4. So you can see the roughness is increasing as I go from right to left. What this max roughness setting does is it provides a cutoff where above a certain value I stop doing the ray tracing. Right now it's set to 0.2, which means I'm only going to see ray traced reflections if my roughness is 0.2 or lower. So you can see I'm getting ray traced reflections on the sphere on the right and on this one here, but from here over I'm actually falling back and just using the cube map reflections. Now this is a really nice performance optimization because the blurrier we get with the reflections, or the rougher the surface is, the harder to tell how accurate the actual reflection is. So I don't know if you can even tell the difference to know that this is a real ray traced reflection here, and this is not. This is actually just a cube map reflection. So as I increase this, the threshold for roughness goes up, and you can see that my sphere here in the middle is changing from a cube map reflection to a ray traced reflection. And as I increase this threshold, I go from a point of some of the scene using cube map reflections to, if I go all the way up to 1, now I'm not using cube map reflections at all. I'm just ray tracing everything. Now this is a little bit dangerous, and I want to describe why, because these reflections that are really blurry are significantly more expensive to calculate. With super sharp reflections, I just need to cast one ray into the scene to capture what that reflection will look like. But with blurry reflections, my reflection angle actually becomes a cone. Instead of just one single ray, it becomes a cone. And the rougher the surface is, the wider that cone is. In order to represent that reflection cone, I actually have to cast a whole bunch of rays into the scene. And the more rays we cast, the more expensive the effect gets. Now this has been optimized, and you can tell by how the effect is kind of wiggling around. Can you see how this is not a static effect, but it's moving? And that's because we're using temporal accumulation. In order to simulate that wide cone of a rough surface, we're casting rays out in random directions every frame and then accumulating them over time to create this effect. And because we're doing this, it's significantly more expensive. So if you want to increase the performance of your scene, try to keep this max roughness value as low as you can. So we only want to ray trace reflections in areas where it's obvious that where it's most obvious that the reflections are actually real. And when we can get away with it, we want to fall back on not using ray trace reflections, but using the light probe cube map reflections instead. All right, so that's our max roughness setting. And I've found that it's good to set that to around 0.2. But if you want to go even lower with that to try to make this like as optimized as you possibly can, that's probably a good idea. All right, the next setting that we're going to look at is called max bounces. Now what this is when I cast rays out into the scene to capture a reflection, what if it hits another surface that's also reflected? Well, at that point, what I need to do is cast another ray. So I've cast a ray to get my reflection, and now I'm casting another ray to get the reflection of the reflection. And a good example of that, right now I've got my max bounces set to 1. And so you can see this spot right here on the sphere that's black. The reason that this is black is because this is something that's reflected. It's a reflective object, but I don't see a reflection of the reflection. And that's because I have my max bounces set to 1. So I only bounce my ray one time, and I don't allow any additional bounces after that. If I increase this max bounces to 2, what you're going to see is this black spot here is going to turn to a chrome spot. And you can see that it didn't actually turn to a chrome spot. And that's because the max roughness cutoff for this sphere is actually below the threshold. So let me scoot over here just a little bit. And if we look at this spot here, you can see that this chrome sphere is reflected in that chrome sphere, and we can see the reflection of the reflection. Now that's pretty fancy. If we increase the max bounces even more, you'll see these two black spots go away. So if I set this to 3, and so we start getting kind of an infinite mirror effect where the ray is bouncing back and forth between these two chrome spheres. However, I'd recommend that you not do this and that you leave max bounces to 1 because bouncing rays all around the scene is pretty expensive, and it's not something that I'd consider worth it. Normally, I mean, you can tell pretty obviously from these chrome spheres that that's an issue, but normally you don't have chrome objects in your scene like this that make the reflections so obvious, and so you can probably get away with just leaving max bounces at 1. All right, now we're going to talk about samples per pixel, and in order to illustrate this, I want to turn up the max roughness a little bit more so that we can see our ray traced reflections on the spheres that have a little bit rougher material. So if I come over here and we look at this, you can see that this is really model-y and it's kind of jiggly and stuff. And that's because of what I was talking about before with the temporal accumulation, because we're actually only shooting out one ray right now per frame and then accumulating them over time. But if I increase this samples per pixel, what we're going to do is increase the number of rays that are sent out for each frame. And the higher that I make this number, the smoother that effect is going to become. And the quality will increase more and more. I'm just going to set it up to 32. And this is totally going to tank my performance, but it's also going to make my reflections nice and smooth. You can see how it's not jiggling anymore. Now, I'm probably getting 1 or 2 frames a second with my samples per pixel at 32. So I definitely don't want to do this. I'm going to leave it, I'm going to set it back down to 1 again. And so all that jiggly modeliness is returning, but like I said before, if we can get rid of that by just reducing the max roughness and keeping the max roughness somewhere around 0.2. All right, the last setting that we're going to talk about today is shadows. And what this means is when the rays get cast out, they will hit the surface and get the reflection on that surface. But also, if I turn this on, they're going to calculate shadows for that location as well. Now, there are multiple settings here. I have it set to disabled for optimum performance. But if we can set it to hard shadows and also area shadows. Now I want you to watch what happens to these reflections. I'm just going to zoom in here on the sphere. Watch here what happens to these reflections when I turn shadows on. So with hard shadows, there's a shadow right there on that seat cast by that pole. And with soft shadows or area shadows, the shadows become significantly softer. You can see how they're kind of blurry looking here. Now this is another one of those features that can seriously hurt performance because it has to calculate both the material color and the shadow. And so we can probably get away with having our shadows disabled just to save on some performance. Alright, so here we have our reflections set to ray tracing. We have our roughness cutoff set to 0.2. So we're only ray tracing objects with a roughness of 0.2 or lower. We have our max bounces set to 1, our samples per pixel set to 1, and our shadows disabled. The only way we could get any more optimal with this is if we set our max roughness to like as low as it can possibly go. And in this case, we're only ray tracing objects that are completely mirror reflections. So these are the settings that I really like to use here: 0.2, 1, 1, and disabled. And still, ray tracing is kind of expensive, ray tracing these reflections, but it does yield some really good results. So if you're making your game for a platform that supports it, or perhaps when the new graphics cards come out this fall, they'll allow us to turn on a lot more of these ray tracing features. But for now, we have to be really conservative with the number of rays that we cast, and just be careful that we're not wasting any resources at all. So that's the tutorial for today. I hope you enjoyed it and that you learned some things about ray tracing. We talked about screen space ray tracing. We talked about, screen space reflections. We talked about light probes or cube map reflections. And we talk about how ray tracing solves all of these problems that these other two methods of reflections introduce. However, ray tracing does come at a cost, and so we have to be fairly conservative if we turn it on for reflections, that we turn the settings down significantly so that we can afford to do this. Well, I hope you enjoyed today's tutorial. If you did, give it a like, and be sure to subscribe to the channel. We're going to talk about another ray tracing feature next week, so be sure to come back and enjoy that video, and we'll see you next week, everybody.